So thank you, Professor Babel, for the introduction. Thank you to the jury members to be here today for this presentation. And hi, everyone. So since my PhD title is quite long and complex, I propose to break it down progressively with you. So first, today we are going to talk about imitation learning for robots. So what does it mean? So today, most of the robotics in the industry is deployed in controlled environments. So usually robots are integrated on production lines designed to integrate the robots. And so those robots are usually executing always the same task, and they are programmed by engineers. However, we wanted to target, during this PhD, we wanted to target industries that still require human labor and that might face labor shortages or high turnover, for instance. And so the problem in this kind of industry is that we have a huge variety of tasks. So if we want to automate all these tasks, we would need to program the robots for each task one by one. And in this kind of industry, operators don't even know how to program a robot. So the solution would be to have robots that could understand new tasks from human demonstrations and with as few explanations as possible, and that could reproduce these tasks using their own capabilities, so their own action space and their own sensors and so on. Okay, but how do we provide human demonstrations to a robot first? So in the literature, there are many ways to provide demonstration to a robot. For instance, using kinesthetic stitching, the human operator can drive the robot to execute the task. Using teleoperation, on the other side, human operator can remotely control the robot to execute the task. But now, with today's artificial intelligence tools, we can wonder if we could maybe directly learn from videos of human doing the task, which would be way more practical in the industry. So now that we understand imitation learning for robots, we need to introduce what we call embodiment and environment-agnostic imitation learning. So let me start with an example. So this is a task that we actually considered during this PhD. So we have a task where the human operator here is taking a paper trash and throw it in the trash bin. So the goal is to understand the task from those human video demonstrations, and then we would like to execute the same task on a robot. So here we have two challenges. First of all, you can see that on the left here and on the right, you have different background environments, different objects in the background, different variations of the objects of interest, such as the trash bin or the paper trash. And at the same time, you also have different embodiments on the left and on the right. On the left, you have a human that is executing the task, and on the right, you have a robot that is reproducing the task. So human, and here we represented single-arm robots, but it could be any kind of robotic platform, bimanual robot, humanoid robot, whatever you want. And the thing is that these two, the human and the robot, first, they have different appearances, but they also have different action spaces, and they follow different trajectories in the 3D space to execute the task. So if we want to learn a task from human demonstration and to execute it on a robot, we need embodiment and environment-agnostic imitation learning solutions. So now that we understand the overall objective of this PhD, we can start to dive a little bit deeper into the components that we use to understand the human demonstrations. So first, what do we mean by understanding human demonstrations? So in our case, we consider that in the scene, we have passive objects on one side. So for instance, the paper trash and the trash bin. And we consider that these passive objects undergo actions from the active objects, and the active objects in the demonstration is the human. So we consider that we need to detect and track the passive objects, and we need to understand what the human is doing with these passive objects. To detect the passive objects, we will leverage tools called language and vision models. And to understand what the active objects are doing with these passive objects, we will use human pose estimation for action recognition. Okay, now we finished the breakdown of this title. So this presentation will be divided into two parts. Actually, in the first part, we will focus on the 3D human pose estimation algorithms that we developed during this PhD. And in the second part, we will present our demonstration understanding pipeline and explain how to transfer a task from those demonstrations to the actual execution on the robot. Note that we also had other research activities, especially on tactile perception of the scene. Actually, also in an embodiment and environment way. We had corresponding contributions in different journals and conferences, but today we will exclusively focus on the visual perception of the environment. So first, let's dive in the human pose estimation solutions. So first, what is human pose estimation and what is the difference between human pose estimation and hand pose estimation? So human pose estimation is the task of locating a set of body joints, such as the wrist, the elbow, the knee, or the hip, and it could be performed in the 2D space if you want to detect the 2D position of the joint in the image, or it could be performed in the 3D space if you want to estimate the 3D position of the human in the predefined coordinate system. The hand pose estimation is very similar, except that it focuses on the joints of the hand. In our case, we need actually both of them. We need human pose estimation, especially to track the position of the wrist of the operator in the 3D space. But we also would like to estimate the pose of the hand of the operator to understand more finely how the operator is interacting with the objects. But actually, human pose estimation and hand pose estimation solutions usually leverage similar algorithms. So during this PhD, we mostly focused on human pose estimation algorithms, but these algorithms can be also applied for hand pose estimation. So now we can start to provide an overview of existing 3D human pose estimation solutions. So the first solution to track the joints of the human body joints in the 3D space would be to equip the operator with a mocap system. So it means that you would put markers and sensors on the operator to track the position of his joints, but it's very not practical and very intrusive, and it's impacting the operator's behavior. So an alternative would be to use a single camera filming the scene. And from this single view filming the scene, we could try to reconstruct the 3D pose of the human. So it's very easy to deploy. You just need to drop one camera in your workspace and it starts to work. But it's quite sensitive to occlusions. For instance, if the operator is hidden here by a shelf, you cannot reconstruct the 3D pose of the operator. And it's also subject to depth ambiguity problems, which just mean that estimating the depth of a scene just from a single view is an ill-posed problem. So alternatively, you can use multiple cameras that will provide new perspectives on the scene. So for instance, here, we have a multi-view setup. And so using this multiple perspective, you can handle occlusions in a better way. And you can also tackle the depth ambiguity problem with these multiple perspectives. But this kind of approach is quite complex to deploy. Why? So actually, for multi-view solutions, we have two kinds of solutions. On one side, we have triangulation-based solution. So triangulation allows to estimate the position of a 3D point, for instance, here, the wrist of the person, from its 2D position in different cameras, filmed by different cameras. For instance, here I have P1 and P2, which is the position of the wrist in these two cameras here. So the problem with this kind of approach is that it needs what we call calibration parameters. So basically, it needs intrinsic parameters, which is information about the cameras, such as focal length or resolutions. So this is quite okay to obtain, but it also requires extrinsic parameters. These extrinsic parameters actually represent the viewing direction of the cameras, how they are positioned and rotated towards each other. The problem is that if you want to obtain these extrinsic parameters, you need a calibration phase. And how do you calibrate such kind of parameters? So usually, you need to empty your workspace, drop a calibration chessboard in the middle of your scene, and now you can start the calibration process. The thing is that once it's done, if your cameras move even slightly, even unintentionally, you need to calibrate again. So you need to empty your space again and start again the calibration. Another kind of solution would be to use deep learning solutions to estimate the 3D pose of the operator from the multiple views of the scene. The thing with deep learning solution is that you would usually train them on a given setup, a given multi-view setup. And this solution doesn't generalize well on new setups. We have an actual experimental validation of this in the manuscript. And so if you want to deploy your deep learning solution on a new camera setup, for instance, on new camera's positions, you would need to retrain your model on this new setup. So why is it a problem? Beyond computational expense of retraining your model, you also need either to use supervised training to train your model. And in this case, you need 3D ground truth poses in your new setup. So you would need to use mocap to collect data to obtain those 3D poses. Or you could use unsupervised training. Unsupervised training does not require 3D ground truth poses to train the model. But usually, we have a paper on that, actually. It requires to calibrate the cameras to define unsupervised losses. And if we need to calibrate the cameras, then we fall back to the problem linked to the triangulation. So if we go one step further, we can wonder if we could train a deep learning model without 3D ground truth, but also without calibrating the cameras. So this will be the focus of this part, the main focus of this part. So we propose the pipeline to do so. So as input of our pipeline, we will have 2D poses detected from the multiple views. Then we will send these 2D poses to a deep learning architecture. Here we use the transformer-like architecture. And the goal of this architecture is to predict extrinsic parameters corresponding to this multi-view setup. We are not predicting directly the 3D pose of the human, we are predicting the extrinsics corresponding to the setup. And using these extrinsics, we can triangulate the pose of the operator to the 3D space. Now, we need an objective to train this model. So we defined two kinds of objectives from this reconstructed 3D pose. So first, on one side, we want the 3D pose, the reconstructed 3D pose, to respect criterions about the human anatomy. So for instance, we would like this 3D skeleton to be symmetrical, and for a given person, we would like the bone length to be constant. On the other hand, we defined additional loss terms to ensure that this 3D pose is actually consistent with the input 2D poses. So in order to define these losses, we can take this 3D pose, reproject it to the 2D space, and then we can start to compare the input 2D poses to the reprojected 2D poses. We can compare it in terms of joint position between input and reprojected 2D poses, in terms of bone length in the 2D space, or in terms of the direction of the bones in the 2D space. So now we have a lot of different loss terms, and we want to define training loss from all these loss terms. So what we did is that we constructed a weighted sum of all these loss terms. So for instance, here we have the 2D loss on the error between reprojected and input 2D poses, the error on the bone direction, the error on the bone length, and the errors in the 3D space. They are all weighted by these lambda here, which are the weights that we'll assign to each of these loss terms. Okay, so now we would like to find these ideal weights such that we get the lower reconstruction error as possible. So in order to do this, we conducted a hyperparameter search. So the hyperparameter search essentially means that we tried different combinations of these hyperparameters, and we kept the combination that allowed to have the lowest 3D reconstruction error. So we conducted this hyperparameter search on the H36M dataset, which is a multi-view human pose estimation dataset with 4 views. Then we can use these best hyperparameters to train our architecture. And then we can start to compare our architecture to other solutions in the literature. So to compare our architecture to other solutions, we will use two metrics. The first metric is called MPGPE. It's the mean per joint error, and it's the raw error, the basic error between the predicted 3D joints and the ground truth 3D joints that we have access to in the H36M dataset. And the PMPGP error is just an MPGP, but after trying to align the predicted 3D skeleton to the ground truth skeleton. So basically, this loss mostly accounts for the quality of the structure of the pose, while this one will also account for error in the positioning of the skeleton in the space. So first, we can start to compare with other existing unsupervised multi-view method that also don't require camera parameters. So compared to the MetaPose, which is a recent state-of-the-art solutions in this category, we obtained similar, even better results, like state-of-the-art results in this category first. And then secondly, interesting, if we compare our approach to our previous approach, which required camera parameters, we can obtain similar or even slightly better results. So even if we don't need camera parameters, we can get similar or better results than with the camera calibration parameters. Now, of course, if we compare to supervised approaches that require 3D poses to train the model, we will get slightly worse results, both in terms of MPGP and PMPGP. And interestingly, if we compare to the best single view approach, okay, we get better results with our multi-view architecture. But for instance, in terms of MPGPE, we only have, let's say, 2 millimeters difference between our multi-view setup and the single view setup here. However, this approach is still supervised, but here the biggest impact on our that might for which multi-view approaches might help are occlusions, and in the H36M dataset there are no occlusions actually. So the question is, can our architecture actually handle occlusions? But also, can we train our model on a new dataset with the hyperparameters that we found on the H36M dataset? So we have actually collected a dataset during this PhD, and we also proposed an annotation tool for this dataset that we published in ICIP 2024. And this dataset is well suited to answer to these two questions, because this dataset is also a multi-view 3D human pose estimation dataset, but it also contains occlusions. So now we try to train our model on our dataset, but using the hyperparameters that we found on the H36M dataset. Now we can notice two things. First, in our dataset, we have a different skeleton format than in the H36M dataset. The skeleton format in our dataset is called the COCO format. And if we use this format to train our model, we will get a strong degradation of performance, especially in terms of MPGP. Here we have almost 12 centimeters error on the reconstruction of the skeleton. But if we adapt the skeleton format in our dataset to match a similar skeleton format that we have in H36M, then we can train our architecture in a way to have similar performance that we got on the H36M dataset. At least we have less degradation in terms of performances. So it means that our model can transfer to new datasets, even from datasets without occlusions to datasets with occlusions, but it's very sensitive to the skeleton format. So this part actually was not in the manuscript, if you are searching for it right now. The whole unsupervised 3D human pose estimation pipeline that I presented here was submitted to ICME 2025 this year, so it's still under review. So now we can move to the part 2. Okay. So now in the part 2, we will dive into our demonstration understanding tool. We will, by the way, see how to integrate 3D human pose estimation tool in this pipeline. And we will later see how to transfer from demonstration understanding to an actual transfer of the task to the robot, to an actual execution on the robot. Okay, first, we need a data set. We need a data set of human demonstration to start working. So we collected a data set with 50 demonstrations of a single task. So this is the task that you saw during the introduction, but I will bring a few more precision on this data set now. So the task is always the same, to take the paper trash and to put it in the trash bin. But the table will always be presented with 3 objects. So the paper with 4 objects, the trash bin, the paper trash, and 2 distractors. The operator should not manipulate the distractors. He should always take the paper trash and put it in the trash bin. In this demonstration, we have 4 different trash bins, 4 different crumpled papers, and all the demonstrations were performed by a single operator using his right hand. So the demos were filmed with a moving camera. We will explain why later. The demonstration was simultaneously recorded using another camera, which was static. It was fixed on a tripod, but mostly for comparison purpose with the moving camera. We'll explain this later on. And we have access to RGB images plus depth maps. So RGB images plus depth maps for each of these demonstrations. So now we can start to dive in our demonstration understanding pipeline. So we have our demonstrations. And as we explained in the introduction, first we want to detect and track our passive objects in the scene. So the trash bin and the paper trash. So to do this, we will use zero-shot object detection models. So zero-shot object detection models actually can detect. Actually, these are models that were trained on millions of images. The one that we use was trained on 20 million of images, but they can adapt to detect objects that they didn't see during the training phase. So this kind of models take as input an image, a semantic information about the target classes that you want to detect. And just by looking at this semantic information, they can guess how to locate these objects in the image. So in our case, we used textual description as the semantic description of our objects. So it means that as input of our vision and language model, we have a textual description, a prompt, specifying that we want to detect the paper trash and the trash bin. We have the image in which we want to detect the objects. And then the model is able to detect these 2 objects as a result. We went one step further. We used a model that is called segment anything that could actually segment the pixels belonging to the objects of interest within the detected bounding boxes. So in the end, you are left with a mask where you have only the pixels corresponding to the objects of interest that are represented. We call this whole pipeline with the grounded dyno, the vision and language model, plus the segmentation part, we call it a grounded SAM, grounded segment anything. This is actually called this way in the literature. So now that we detected our objects of interest in the first frame of the video, we want to track these objects in the later frames of the video. So we used an off-the-shelf object tracker to track those objects in the later frames of the video. So in the end, we are left with a video that features only the position of the pixel of our object of interest here. So I want to point out that we investigated different prompting strategies to improve the detection performance especially of the vision and language model that detects the objects from the prompt. So we presented a paper on iROS 2024 on this contribution. And I will not dive into this contribution today, but I will explain just it in a few words. It just allowed us to correctly annotate 76% of our demonstrations when using our prompt engineering solutions, while using naive prompt engineering solutions, so just asking for the trash bin and the paper trash, we could only annotate correctly 52% of our demonstration automatically. So now that you can correctly detect the objects of interest, one last step is to try to project those objects as a 3D point cloud. Because ultimately the task during the execution on a robot will happen in the 3D space. So it brings more information to understand the task if we can project it to the 3D space. So since we have access to depth map in our demonstrations, we can actually take those 2D segmentations and project them as a 3D point cloud where you only have your two objects of interest, the paper trash and the trash bin. Okay, now we can detect and track our passive object in the scene. But what is actually the active object, the human? What is he doing with these passive objects? So to understand this, first we manually annotated a set of primitives in our demonstrations. So we annotated 3 primitives. We considered that first the human operator is reaching the paper to grasp it. Then the operator is moving towards the trash bin, but above it to avoid collision with it. And then the operator is kind of moving down to the trash bin in order to release the paper inside it. But we would like to understand this action in a more subtle way. Actually, we would like to understand exactly how the operator is grasping the paper, with which position and how he's grasping the paper. We would like to understand how high the operator is moving above the trash bin to release the paper, to avoid collision, sorry. And we would like to understand where exactly the operator is throwing the paper inside the trash bin. So to do this, we can use hand pose estimation. We actually used hand pose estimation to estimate the position of the operator in this 3D scene. So since we have access to RGBD images in our dataset, we leverage an RGBD-based 3D hand pose estimation model to recover the position of the hand in the scene. Then we perform one more step on this hand pose estimation. We summarized the human operator as the average position of his fingers joint. And to representing the operator in such a way, it's quite interesting because we can similarly represent a robot in the 3D scene. Because in the case of the robot, we can have access to the position of its tool and represent the position of his tool directly as a 3D point in the space. So now we have a representation of the human operator and of the robot in the scene that is similar. So this is key for the embodiment agnosticity because we need to represent the scene in a way that is agnostic to the embodiment, whether it's a human or a robot. Okay, now we can zoom in on one of the primitives, reach and grasp the paper. So this primitive is made of n frames. And what we would like here is to train a deep learning model to predict the position of the operator in the last frame. We would like the deep learning model to be able to predict this position for each of the frames that come before the last frame. So for each of these frames, for instance, if I take the frame T2, I put it as input of my deep learning model. The deep learning model should be able to predict where the operator is going relative to the object of interest in order to achieve the reach and grasp the paper primitive. Okay, if we can achieve this, then this deep learning model can be similarly deployed once it's trained on human demonstration. It can be deployed on videos of a robot trying to execute the task, since we have a representation of the scene that is agnostic to the operator and agnostic to the background environment. If I put similar representation as input of my deep learning model, it should be able to predict similar outputs. Then, if we can train our deep learning policy our deep learning model in such a way, we can start to plug it to a robot in simulation and see what happens. So first, in the simulation, you would have an initial observation of the scene where your robot is just standing straight and you have your object of interest on the table. Then this image can be sent to our detection and tracking of passive objects, and we can extract our 3D representation of the scene. And then from this representation of the scene, our deep learning model should be able to predict where the robot should go in order to execute the task. So this is actually the 3D point that the robot should reach next in the scene. This 3D point can be sent to a path planner that can drive the robot to the desired point. Then we can execute this in the simulation, and we will get a new observation in the scene, from which we can again extract an observation, send it to the deep learning policy, and so on until the task is executed. So actually, in our case, we choose to use a diffusion policy, especially because it's very interesting because it's very robust to hyperparameter changes. So it mostly means that we can use this policy without hyperparameter tuning on our use case. And it can also handle high dimensional action spaces, which can be interesting if we want to later extend our work to more complex action spaces. If you want more details on the training procedure of our diffusion policy, we actually published a paper on IROS 2024 on this topic. And so now I will dive in the results of the transfer to the robot. We will see if it actually worked to train our policy on the human demonstration and if we could actually transfer it and deploy it on the robot. So we have three situations here. The first situation is the training pipeline that we explained before. So we will train our diffusion policy to predict the position that the operator will reach at the end of the ongoing primitive, as we explained before. And we train this diffusion policy on data coming from a moving camera. The second situation, the second setup, we similarly train the model to predict where the human operator is going at the end of the ongoing primitive, but we do it from data that we collected using a fixed camera. And then we have a third setup where we also use moving camera data collected from the moving camera, but this time we are not predicting the position that the operator reaches at the end of the primitives. We are not using these primitives anymore. We'll train the model to predict the position of the operator in the very next frame consecutive to the observation at a given time. So I have the observation of the scene here, and I want my diffusion policy to predict where the robot should be right after. So it's predicting delta positions of the robot. So we can see that with our proposed pipeline, we can get 20% success rates in simulation on a robot while it was trained on human demonstrations in this kind of real environment. If we use the fixed camera, we could only get 0% success rate. So it means that if you use a fixed camera to collect your demonstrations, your model will be, in a way, overfitted to the camera viewpoint that you have in your data. And then it cannot deploy in a new viewpoint that you would have in your new setup. And lastly, if we don't use primitives, if you just predict delta position to drive the robot progressively in the scene, you also get 0% success rate. So this one might seem a little bit more weird. Actually, we suppose that the human pose estimation here might be actually more noisy than just the delta position between two adjacent frames. So if the error on the hand pose estimation is greater than the actual delta position of the hand between two frames, then your data is too noisy to be able to learn something. And then we conducted another experiment. So we took our first setup here, and we trained it on our human demonstration with a moving camera using the primitives. And then we got the 20% success rate that I mentioned before. Then if we take 10 successful executions from these 20% successful rollouts, we put these 10 successful executions in addition to the 50 human demonstrations in your training data. If you retrain your policy on such data, then you will get 34% success rate. But then it can start, you can loop like that again and again. As soon as you deploy your model and get this 34% success rate, you can again take, let's say, 10 more successful execution, put it again in the training set, and improve again and again the performance of your policy. Okay, now why 20% success rate? It seems super low. Okay, so there is a gap between the real and the simulated sensor. In the end, we are not left with the same point clouds when we are using the iPhone camera or the simulated sensor in the simulation that we are using. So in the end, we have a representation that is not completely agnostic to the environment in the way that it is not agnostic to the sensor that is used. Then another quite funny, actually, factor that we highlighted in our demonstration is that the human is actually leveraging his velocity to throw the paper trash inside the trash bin. If the robot tries to reach the same point above the trash bin, but without the same velocity, the paper trash will just fall just aside the trash bin. So this is maybe a missing modality that we have in our pipeline. And then, of course, there is the last step. We used single view human pose estimation to estimate the position of the human in the scene, which was quite noisy. But of course, we will talk about that in the perspectives. So as a conclusion, we have a pipeline here that we developed, where first, we propose some multi-view unsupervised solutions that can be trained without calibrating the cameras. We didn't use these particular algorithms in this pipeline, but I will explain it in the perspective later. Then we used we investigated some prompt engineering strategies. We investigated some prompt engineering strategies, to improve the detection and tracking of the passive object in the scene. Additionally, we actually validated that the deployment from a model that is trained on human demonstration could actually be deployed in a simulation on a robot with the limitation that we highlighted before, but still we highlighted that it was feasible. So in a way, our representation is actually embodiment and environment agnostic. Then we also highlighted that having a moving camera during the demonstration collection seems crucial if you don't want to have a model that is overfitted to a single viewpoint. And lastly, using the primitives that we annotate, using the primitives such as reach and grasp the paper or reach above the trash bin to release the paper, using this primitive was also crucial to achieve a non-zero success rate, basically. Okay, these contributions were disseminated in different journal or conference papers, depending on the different topics. Some on human pose estimation, some on imitation learning, and we had some on tactile exploration that I didn't focus on today. We also had other contributions, especially on action recognition. Okay, now the perspectives. So first here, we didn't use our multi-view unsupervised setup to annotate the pose of the humans in our demonstrations. But it could be interesting to investigate to use such multi-view setup to annotate our demonstrations. We could have our RGBD camera as one of the viewpoints, and maybe two more RGB cameras on the sides, and that might allow to reconstruct more finely the pose, for instance, the pose of the human hand in the scene. This is actually a trial, one trial that we made to triangulate the pose of the hands from multiple views in the scene. But we said that we required at least one viewpoint that is moving to collect our demonstrations. But can we use a viewpoint that is moving in this architecture? Can we still use this architecture to predict the extrinsics if the actual position of the camera is moving during the recording? So this is something that could be investigated in the perspective. Can we use this architecture, first of all, for 3D hand pose estimation, but also when one of the cameras is moving? Then we have a limitation on the scene representation. Actually, our scene representation is not, our scene representation is not completely environment agnostic. Here, suppose that an object appears during the deployment of the policy. Now I want to move, let's say, my paper trash towards the trash bin, so from A to B, but I have an object in the middle, and this object is not represented in our 3D representation because we only focus on the object of interest. So there are actually existing solutions that can plan a path from point A to point B while constrained to avoid occlusion, knowing the 3D map of the scene. But these solutions, they are not working if the obstacle is moving. So if you have a dynamic obstacle moving in the scene, we might need to train, for instance, some more smarter path planning. So for instance, training path planners with dynamic obstacle avoidance solutions. Okay. Then we also had a limitation on the primitives annotation because we annotated our primitives manually. So we actually had other contribution on action recognition. And we could wonder if we could extend these action recognition solutions to maybe detect actions that are actually relevant to robotics, because most of the action recognition solutions that are existing today, they are focusing on a lot of different actions, but not specifically related to primitives that can be executed on the robots. And we could also further explore if we could use large vision and language model to locate the primitives start and end in the demonstration by interacting with this kind of model on the video. So, okay. And then we have, we have a lot of other limitations on the actually embodiment agnosticity of our approach. So first of all, as I said, we had demonstrations that were performed with single arm and reproduced by single arm robotic platforms. So we could extend it to bimanual interactions. And we could also try to incorporate additional modalities, as I said, such as the speed of the operator in the scene, because it was clearly lacking in our demonstration understanding pipeline. But we could also we can also wonder if we could add some other modalities related, for instance, to the force that the operator is exerting on the objects, because robots are actually sometimes controlled in position, but sometimes they are controlled by torque. So this is also another limitation of our pipeline that might be interesting to investigate. Okay, so thank you.
Bien, merci pour votre présentation. Je vais également commencer par remercier les donc Kelly et Patrick pour avoir invité à ce juriste et puis pour leur accueil chaleureux ce midi. Donc, concernant votre présentation, elle était vraiment très claire, didactique, avec plein d'informations. Des vidéos aussi qui aident à la compréhension par rapport au manuscrit. Et j'ai aussi beaucoup apprécié que vous n'ayez pas présenté tout le travail que vous avez mis dans votre manuscrit, parce que vous avez incompréhensible. Donc, vous avez choisi de supprimer les parties entières de votre travail. Et je crois que c'est un bon choix de manière à garder un peu l'histoire à côté. Donc, en tout cas, c'était un choix judicieux. Donc, concernant le sujet, c'est un sujet très, très compliqué, très multidisciplinaire aussi. Du coup, bah, on a vu que vous avez touché à beaucoup de choses. Donc, ça a demandé des compétences dans plein de domaines. Donc, dont des domaines d'ailleurs qu'on n'a pas vu, hein, tout l'aspect robotique et vraiment l'implémentation sur robot, c'est pas rien.
Ouais.
C'est beaucoup de temps, c'est souvent là d'ailleurs qu'on passe le plus de temps.
Ouais.
Donc, un sujet très difficile, très intéressant, avec beaucoup d'informations. Je pense que l'industrie du futur, notamment,
Ouais.
l'attente de ce genre d'avancée. Donc, intéressant, plein d'attentes, très compétitif, avec beaucoup de chercheurs qui cassent un peu les dents là-dessus. Et malgré la compétition, ben, vous avez réussi à amener des avancées, vos avancées. Félicitations pour ça.
Merci.
Qu'est-ce que j'avais noté aussi? Non, bah, à peu près tout pour le contexte général. Donc, maintenant, je vais passer à mes questions. Une première, alors j'avais pas de question sur l'approche tactile.
Ok.
Je ne vais pas les poser du coup, mais vraiment, j'ai adoré cette partie.
Vous pouvez y aller, hein. Allez-y. Allez-y. Hein.
Je me concentre là-dessus. Sur le prompt engineering, donc c'est vrai que ça améliore, mais finalement, je trouve que ça enlève un peu l'aspect invariant à l'environnement si on est obligé de décrire à l'avance des objets qui pourraient perturber.
Ouais.
Donc, votre, c'est un peu mitigé finalement, je trouve, les résultats. Bah, ok,
Ouais.
ça améliore, mais quel est votre sentiment là-dessus?
Alors, effectivement, avec les modèles de Vision and Language Model qu'on a utilisés à l'heure d'aujourd'hui, on avait besoin de s'aider avec du prompt engineering pour améliorer les performances de détection de nos objets. Donc, alors déjà, première chose, ça c'est une limite qu'on a à l'heure d'aujourd'hui, mais je ne serais pas étonné que même déjà si je retestais les nouvelles versions des modèles aujourd'hui, j'aurais peut-être même presque plus besoin de ce genre de prompt engineering pour détecter les bons objets en fait. Donc déjà, ça c'est une chose. Ensuite, là, j'ai fait du prompt engineering à la main. C'est-à-dire que moi-même, j'ai essayé de me dire, tiens, ici j'ajoutais autre chose que mes objets d'intérêt dans mes prompts. Je vais venir essayer de détecter tous mes objets pour être sûr que mon modèle détecte tout et ensuite je les filtre. Donc ça, je l'ai fait, c'est vrai que je l'ai fait à la main. Après, on pourrait se dire, bah, plutôt que de moi-même taper ça à la main, bah, je pourrais utiliser un autre VLM, un autre Vision Language Model, auquel je lui donnerais juste mon image brute et je lui dis, bah là, qu'est-ce que tu penses qu'il y a dans cette scène comme objet d'intérêt? Donc là, le VLM me ferait des propositions d'objets qu'on pourrait trouver dans la scène. J'envoie ces propositions-là à mon Grounded Segment Anything. Mon Grounded Segment Anything essaye de me faire une segmentation. Cette segmentation, je la renvoie à mon VLM et je lui redemande bah, maintenant, qu'est-ce que tu en penses de cette segmentation? Est-ce que cette segmentation, on ne pourrait pas encore l'améliorer en faisant un prompt différent? Et donc, au lieu de moi-même faire le prompt, bah, je pourrais utiliser un VLM pour faire le prompt. Alors, ce genre d'approche, je ne les ai pas encore vus. Par contre, j'ai vu un truc similaire c'était sur Heroes, justement, l'année dernière, où ben, il y avait un gars qui présentait un poster. Et en fait, ce qu'il proposait, c'était d'utiliser un VLM, où en fait, ben, il voulait détecter ces objets d'intérêt dans la scène. Et en fait, donc, il donnait l'image de la scène à un premier modèle, et ce premier modèle venait mettre des labels sur les différents objets de la scène. C'est-à-dire que là, le premier modèle, il est capable de dire, bah là, je crois qu'il y a un objet en 8, il y a un objet en 9, il y a un objet en 7. Peu importe, je ne sais pas trop ce que c'est, mais ça, derrière, je peux l'envoyer à un deuxième VLM, donc c'était un chat GPT 4V, et je lui demandais bah, maintenant quel objet je dois venir attraper. Ou on pourrait même lui demander quel objet je dois venir attraper si je veux donner un coup de marteau, quoi. Et donc, en fait, en associant comme ça différents VLM, on pourrait s'abstraire de cette phase de prompt engineering, en tout cas à mon sens. Et encore une fois, est-ce qu'on aura encore besoin du prompt engineering dans 6 mois? Est-ce qu'on en a encore besoin aujourd'hui? Ça, j'en suis pas sûr.
Dans l'estimation des causes,
Ouais.
on va parler là, mais vous utilisez plusieurs images pour estimer la cause à l'image centrale.
Ah oui, ouais.
Du coup, ça fausse un peu les résultats. quand vous comparez à d'autres méthodes qui utilisent une seule image. Peut-être qu'il y a un espèce de filtrage temporel.
Ouais.
Et voilà votre sentiment là-dessus.
Alors, le fait d'utiliser, en fait, donc j'ai plusieurs points de vue sur ma scène, mais sauf que effectivement, alors, est-ce que j'ai mon architecture? Je vais la montrer ici. Et tac. Effectivement, là, sur mon architecture, si je remets un gros plan, donc j'ai plusieurs vues sur ma scène. Et effectivement, pour chaque vue, on ne va pas uniquement prendre une pause à un instant T, et on va plutôt prendre une succession de pauses. Donc, c'est comme si on avait une petite sous-vidéo pour chaque vue en entrée de notre modèle.
Parce qu'il y a des méthodes, enfin, les autres méthodes, je pense, qu'on travaille avec une feuille.
Ouais, ça, il y en a. Mais effectivement, mais l'avantage d'avoir ce genre de méthode, c'est que, ben, en fait, on peut, entre guillemets, le modèle peut comprendre une espèce de smoothing, ce qu'on dirait ça en français, de lissage.
C'est normal que les meilleurs résultats avec le conflit que les
Ouais.
autres pas.
Après, comment dire, comment dire, dans ce tableau-là, on se compare, bah, par exemple, la meilleure single view à laquelle on se compare, elle est la 135 time step en entrée, quoi.
Ouais.
Donc, effectivement, nous, avec cette time step, on est quand même raisonnable et surtout, bah, en fait, les résultats que je donnais tout à l'heure, en fait, on venait comparer notre approche avec, bah, par exemple, avec une approche similaire qu'on a eue, mais avec les paramètres de calibration, on se compare avec le même nombre de frames en entrée, quoi. Donc après, effectivement, c'est compliqué de venir se comparer à toutes les approches possibles avec tous les nombres de frames possibles. Donc après, on s'est fixé, on voit en fait ici, on a beaucoup de t égale 7 parce que enfin, dans la littérature, en fait, on trouve déjà plein de résultats avec ce nombre de frames-là, en fait. Et, ouais.
Parce que les autres font ça.
Ouais. Enfin, après, non, mais après, c'est une super bonne question. C'est-à-dire qu'on pourrait rajouter de plus en plus de frames, mais après, il faut se dire que, admettons qu'on mette 135 frames. Ça veut dire que la personne doit commencer à rentrer dans la scène. Et on doit attendre 135 frames avant de commencer à faire une détection qui est peut-être potable. Donc, en fait, plus on va mettre de frames, bah, plus on va aussi avoir un modèle qui ne va pas être si facile que ça à déployer non plus, en fait. Et derrière, ouais.
Mais vous n'avez pas pu regarder l'évolution des résultats?
Alors, si on avait des ablations mais alors on avait dû faire. On s'était limité jusqu'à 23 frames, il me semble. Alors effectivement, plus on ajoute de frames, plus on vient gagner des pouillèmes, des petits millimètres. Mais en fait, entre 7 et 23 frames, on va pas avoir une différence significative en fait sur l'estimation de pause, quoi. Je pense que ça va même mettre, on va avoir plus de désavantages que d'avantages à mettre vraiment plus de frames en entrée de notre modèle, quoi.
Et bien, question sur cette partie-là. J'ai vu un thème en décembre à un cours échoué qui fait un peu la même chose. Mais eux, ils utilisaient des pauses de synthèse.
Ok, ouais, des datasets de synthèse.
Quand vous partez datasets, et vous travaillez sur les pauses 2D.
Ouais.
Et en fait, on peut générer des pauses 2D artificielles.
Ouais.
C'est beaucoup plus facile que gérer des images de synthèse.
Ouais, c'est sûr. Mais après, du coup, alors, enfin oui, du coup, j'ai vu ce genre de pause de synthèse et de génération en fait de pause synthétique. Mais derrière, enfin, on aura toujours la critique de savoir ben, est-ce qu'on est vraiment représentatif. Par exemple, ici, dans mon cas, alors je sais pas si j'ai une bonne image. Enfin, par exemple, dans mon cas, ici, j'ai des occlusions. Est-ce que je peux vraiment avoir quelque chose de représentatif sur des poses de synthèse qui sont vraiment représentatives de l'estimation de pose 2D que j'aurai sur une image où j'ai des occlusions, en fait. Donc, c'est-à-dire que ici, dans cette image-là, en fait, j'ai un estimateur de pose 2D qui vient me faire une estimation de pose qui contient du bruit, en fait. Il contient un bruit qui va dépendre des occlusions, qui va dépendre de mon capteur, de la distance de mon capteur à la scène. Si je travaille avec une pose de synthèse, je prends ma pose 3D, véritable terrain 3D, je la reprojette en 2D, j'obtiens mes poses 2D. Mais à la limite, j'ai envie de dire, si on fait ça, je prends mes poses 2D, je refais une simple triangulation et je vais obtenir ma pose 3D parfaite. Parce que si on considère que mes paramètres de calibration sont plutôt propres, mes poses 2D sont parfaites, alors ma triangulation sera presque parfaite. Donc, c'est quoi l'intérêt de mettre un modèle de deep learning en place si en fait nos poses en entrée, si nos poses 2D sont parfaites? En fait, l'intérêt d'avoir aussi l'aspect deep learning, c'est qu'il est capable de gérer différentes erreurs dans les détections 2D. Et ces erreurs-là seront peut-être différentes d'une vue à l'autre, en fait. Ouais. Et ça, on ne l'aura pas forcément sur des poses de synthèse. Après, avoir des poses de synthèse pour se construire une énorme base de données pour faire du pré-entraînement, c'est top. Surtout, ici, moi, je posais la question, est-ce qu'on peut commencer à travailler avec, avec des vues qui bougent? Dès qu'on va vouloir commencer à monter un setup pour faire des véritables acquisitions de données avec des caméras qui commencent à bouger, en fait, ça peut être pratique de commencer à faire ça avec des poches de synthèse, de simuler des points de vue qui bougent, en fait. Donc, c'est beaucoup plus facile de venir, comment dire, prototyper avec des poches de synthèse. Mais derrière, je pense que c'est toujours crucial de venir vérifier expérimentalement sur des vraies données, quoi.
Maintenant, sur la dernière partie, euh, donc vous proposez d'utiliser des méthodes à base de points d'intérêt pour découper l'action, finalement,
Ouais.
l'action. Cette partie est faite à la main.
Ouais.
Et alors, ça m'embête parce que, ok, on est invariant à l'environnement, il y a plein de choses, mais finalement, on n'est plus invariant à la tâche. Il faut que quelqu'un humain, à l'avance, dise, d'ailleurs, qu'il y aura un obstacle et que la première partie, ça va être ça. Donc ça m'embête un peu. Donc, dans les perspectives, vous proposez d'utiliser des méthodes de prévision d'action. Mais à mon avis, la difficulté, c'est pas tellement de reconnaître, ça va être de faire les clusters, de faire automatiquement.
Ouais, ouais, ouais.
Est-ce que vous avez des idées, des petites pistes pour essayer de faire en sorte que ça soit automatisé?
Alors, ce que vous demandez, c'est que, enfin, selon vous, la difficulté, c'est pas tant de reconnaître les actions qu'on a dans la vidéo, c'est plutôt d'être capable de reconnaître quand est-ce que les primitives commencent et se terminent, en fait. C'est ça que vous...
Vous avez dit qu'il y avait trois primitives.
Ouais, ouais.
Comment faire cette partie de la vidéo?
Ah, ok. Alors,
Finalement, c'est trois actions différentes.
voilà, ouais. Alors, en fait, enfin, selon moi, cette partie-là, c'est vraiment pas la plus difficile de se dire, en fait, je sais que sur mon robot, je peux faire telle ou telle primitive. Ouais, admettons que sur mon robot, je puisse atteindre un point à attraper, ou je peux, en fait, j'ai des primitives bien prédéfinies. Je peux très bien donner cette vidéo à un modèle, encore une fois, de vision plus langage, et lui dire, par exemple, j'envoie la vidéo ou mes images sur ChatGPT 4o, par exemple, et je lui demande, en fait, moi, mon robot, il peut faire trois primitives. Là, trouve-moi ces trois primitives-là dans les vidéos que je te donne là. Et quand est-ce qu'elles commencent, quand est-ce qu'elles se terminent. Donc ça, je pense que sur de l'image, on commence à pouvoir. Enfin, moi, j'ai joué un petit peu là, avec Patrick, justement. Il m'a parlé d'un modèle il y a 2 semaines. Je ne l'avais même pas vu. C'est un peu un concurrent des versions de ChatGPT 4o, en fait, où on peut donner en entrée du texte et de l'image. Mais il est open source, donc on peut vraiment jouer facilement avec. Et sur de l'image, il est vraiment déjà pas mauvais pour commencer à discuter sur une image et à discuter sur qu'est-ce qui se passe dans la scène. Est-ce que le gars, là, qu'est-ce qu'il est en train de faire? Est-ce qu'à partir de ça, peut-être que mon modèle pourra me dire, là, en fait, il est en train de mettre une boule de papier dans la poubelle. On peut aller plus loin dans les questions. Comment il le fait? Comment il le fait? Bon, la première étape, c'est il a besoin d'aller attraper le papier. En fait, en interagissant automatiquement avec des modèles de VLM, je pense que ça pourra être fait automatiquement. La question, c'est, pour l'instant, là où on est un peu limité, c'est que les modèles de VLM sur la vidéo, puisque j'en ai testé, j'avais testé les vidéos Lama, je ne sais pas si ça vous parle, c'est un petit peu comme ce que je viens de dire, mais sauf que ça peut fonctionner sur de la vidéo, et c'était quand même pour l'instant relativement mauvais. C'est-à-dire que je lui demandais sur une vidéo quand est-ce que telle ou telle action commençait et se terminait, et franchement, c'était plutôt médiocre. Mais encore une fois, enfin, moi, au début de ma thèse, ce genre de modèle type InternVL, j'y avais même pas accès. Moi, quand je voulais entraîner un modèle à détecter des nouveaux objets d'intérêt, il fallait que je les annote à la main et que j'entraîne un modèle dessus. Aujourd'hui, j'ai juste à donner un prompt et éventuellement à venir cliquer sur mes objets pour finir la segmentation. Donc, je pense que vraiment, dans même un an ou deux, je ne serais pas étonné de voir un modèle qui fonctionne très bien sur la vidéo et auquel je pourrais juste demander, en fait, maintenant, moi, mon robot il peut faire trois primitives, trouve-les-moi dans cette vidéo-là, dis-moi quand est-ce qu'elle commence et quand est-ce qu'elle se termine, et en fait, le modèle, il y arrivera, quoi. Donc, en tout cas, je dirais pas... Ouais. Comment?
Je suis pas sûre qu'aujourd'hui, on puisse le faire avec ChatGPT.
Sur la vidéo, non. Non, non, sur des images, alors... Comment?
À image fixe, ça paraît compliqué de savoir.
Alors, à image fixe, on peut uniquement poser des questions sur ce qui se passe dans la scène à un instant T et éventuellement sur ce qui peut se passer dans le futur et ce qui a pu se passer dans le futur, dans le passé, pardon. Mais on peut quand même poser pas mal de questions sur une image. Enfin, par exemple, ici, sur une image, si je lui demande qu'est-ce qui se passe, je pense que vu le positionnement de la main, il est capable de comprendre que là, la personne, probablement, elle va se diriger vers un des trois objets. Si on est déjà capable de faire ça sur l'image, je ne vois pas pourquoi on pourrait, fondamentalement, pourquoi on ne pourrait pas étendre ça à de la vidéo avec un tout petit peu plus de puissance de calcul. au lieu de le faire sur une image fixe, l'étendre sur de la vidéo pour pouvoir. Donc voilà. Mais
Directement, ça prend la vie.
comment? Ah ouais. Ben, alors non, mais alors ça par contre c'est une très bonne, enfin c'est une très bonne question. On a des, alors on a des modèles qu'on pourrait qualifier de large action models. En fait, tac tac, j'ai trop de slides. Il y a une dataset qui a été collectée par une multitude de labos. Alors je ne sais plus en quelle année elle est sortie, assez récemment, et dans laquelle on a et voilà, une collaboration de 34 labos de recherche et dans laquelle ils ont collecté, par téléopération, ils ont collecté des millions d'épisodes sur des robots. Et en fait, ils ont collecté voilà, 527 skills, ils ont 60 datasets qu'ils ont réunis entre elles sur différentes plateformes. Et en fait, à partir de ça, bah, ils ont entraîné ce qu'ils appellent des policies généralistes. C'est-à-dire que ces policies-là, bah, en fait, c'est un peu comme ce qu'on fait avec des Vision and Language Models, enfin, ceux dont on parlait avant, mais appliqués à de la prédiction d'action. C'est-à-dire qu'en entrée, bah, je peux venir donner, par exemple, une image de ma scène, une description de ce que je veux faire dans cette scène-là, et mon modèle, il est capable de prédire des actions sur tel ou tel robot, parce que dans la base de données d'entraînement, il a vu tout un tas de robots. Donc en fait, la question, elle n'est pas si idiote que ça, parce que en fait, on est déjà en train de le faire. Les large action models, j'en fais déjà en fait.
Générer les comportements d'avatar, avatar en interaction avec un humain.
Ouais, bien sûr. Bah ouais, bien sûr. On peut utiliser. Bah, d'ailleurs, en fait, la diffusion policy que j'ai utilisée là sur mon cas d'application, bah, on s'est amusé à l'utiliser avec UJ sur un cas d'application complètement différent dans le labo, qui était sur de la prédiction. Enfin, en fait, on générait des trajectoires humaines à partir de. En fait, on avait des données, des trajectoires en VR, d'humains en VR, et on s'amusait à générer des trajectoires similaires avec des comportements similaires pour du comportement humain. Donc, je sais pas du comportement robot, mais effectivement, on veut modéliser du comportement, on veut générer du comportement, quoi. Effectivement, ouais, c'est le même genre de tâche.
Une toute dernière question. J'ai l'impression que vous avez été un peu pris par le mot à la fin.
Ouais.
Du coup, si vous aviez à refaire les trois thèses,
Ouais.
il y avait pareil, il y avait directement à la fin.
Tu vas directement à la fin? Ah, c'est une bonne question.
Il y a plein d'endroits où vous avez amené des choses, hein, vous
Ouais.
avez pu amener des Italiens, utiliser l'italien.
Ouais.
Sur l'apprentissage des pays, par exemple.
Par exemple, ouais. Donc, bah, par exemple, ouais, franchement, ça peut le faire. Parce qu'en fait, ce qu'on voit pas non plus, c'est que par exemple, on se dit, bah là, on a tout un pipeline de compréhension de démo et de reproduction sur un robot qu'on a développé peut-être un peu plus à la va-vite que toute la partie estimation de pause. Mais en fait, sur toute la partie, là ici, j'ai présenté la partie estimation de pause comme un outil pour l'imitation learning. Mais en fait, on l'a aussi utilisé avec un autre doctorant chinois avec qui je collaborais, mais là, ce coup-ci, sur l'estimation d'ergonomie. Bah, je peux le montrer, je crois que j'ai une vidéo. En fait, la dataset qu'on a collectée, dont je parlais tout à l'heure, bah, en fait, elle vient avec des labels d'ergonomie. C'est-à-dire que la personne, on sait ce qu'elle fait dans la scène, et on sait quelle position, est-ce qu'elle maintient une position plus ou moins ergonomique dans la scène pendant qu'elle travaille. Et en fait, bah, moi, je trouve que pour tous ces cas d'application-là, bah, ça valait quand même vachement le coup d'investiguer tout ce qu'on a fait sur l'estimation de pose 3D. Et puis en plus, franchement, bah, très personnellement, le montage de ce setup-là, même d'un point de vue engineering, c'était assez challengeant parce qu'on s'est fixé des contraintes qui étaient assez challengeantes dessus et en fait, c'était aussi vraiment plutôt cool à monter. Voilà, mais voilà, d'un point de vue scientifique et technique, oui, je pense que je referai ça quand même. Ouais. Ouais.
Alors, plein de questions, mais j'ai un train à prendre.
À 18 heures.
Merci, félicitations pour tout le travail.
Merci.
Merci beaucoup pour laisser la parole à Victor. Et le deuxième entretien.
Ok, merci. Je vais parler un petit peu en français d'abord, mais après on parle anglais, d'accord?
Ça marche.
Bon, parce que mon français est un peu limité pour cette discussion.
Ça marche.
De toute façon, on peut commencer pour une salutation au jury, à la présidente. On va dire merci pour l'invitation, comme vous l'avez. Merci Patrick, et merci Kenny. Je veux aussi saluer l'assistance et bien sûr à vous, Kevin, et le féliciter pour tout ce travail. Et maintenant, je parle en anglais.
Ok.
C'est bien pour vous. OK. Thank you very much. Now, in English, I think it is a good put on something. The idea, as I don't have much time, we could discuss this hours and hours because it's a lot of work here. But my idea would be to give some general comments on the work, because it's one of the things that struck me the most, and get your comment on that. And then also, and the most important part, the contents and the contribution of your work, what I got as the most important for me. Perhaps you disagree, but I'll give you the chance. And then the last part of our interaction, I have some questions, because I have some doubts. One of them Katrina is already, but I've made that.
Okay.
Thank you. Well, first of all, I would like to talk about the document and the work. The document is very well organized. You have a good global introduction with your definition of your research with the usual research questions. By the way, I like the presentation. I like the first 5 minutes that you took to explain everyone what was the problem. That's very important when you communicate with someone. So congratulations on that. And then the more technical details for the jury. But the first 5 minutes were interesting to explain the title. It's a good approach. I recommend it to my students too. But going back to the document, you have good things on the document that help you reading the document. Very long document and very dense in some parts. It's becoming not very common to a document with 200 pages or more. Although I have a student that has a thesis with 500 pages. No more of the jury. Never repeat that. Well, actually, there were 475, not 500. Okay. Your document is okay. It's well organized. You have an overview of the beginning of each part. That was very important to me. So I understood it, and then I can reread it again, and that's important because sometimes you have to go back and read again. You have an introduction and conclusion on each chapter. That was also a nice option. And the conclusion is well organized, the global conclusion, so it helped a lot. And you have relevant set of analysis for information. It's not common to see from many, but it's very good. And you supported most of your work, chapters, with your own publications. I like that because that shows that what you've done is interesting and it's valid, it's recognized by the others, and it influences your work. Even if you didn't mention everything here in the presentation, it was impossible, of course. I like that approach. Also, you have a good set of publications in top conferences, very good conference, and also in journals. And I realized that you have also recently participation in other transactions. So congratulations on that. That's the acknowledgement of the community. Okay. The writing is pleasant to read and generally relevant. There's some minor errors in and but I'm not stressed and they're not that relevant. Sometimes if you get to reading, writing in English, you wrote it in French, objectif instead of objectif. Crucial with a T instead of a C, but that's not relevant. That's the minor things. I will not waste time on that. There are those some concerning the photo. There are minor issues, like in page 33, when you report to equation 2.1, you mentioned that distortion parameters can also be added to the increasing parameter matrix. I don't think I agree with that because distortion parameters, in page 33, when you report to equation 2.1, it's not very relevant, but in a PhD thesis, we can clarify. I don't know what you wanted to say, but as far as I know, the distortions are not in certain increasing parameters. They are a non-linear operation that you do outside the parameter. That's a small detail, but well, when you reach this level, the small details can be struck. And the same also happens, I think, in the next page when you have the multiplication of the matrix extrinsics. You have on one side the 3 per 1 vector, and on the right side a 4 per 1 vector, and you have the inverse of matrix, which leads you to understand that's the inverse of a non-square matrix. Okay, don't distract your readers with these things. I know what you want to be, of course.
Okay.
That's not true. That's what is written. So just a small advice.
Yeah, thank you.
Don't take it too seriously. These comments that I'm doing, I'm not I'm evaluating your work. It's small details that perhaps you can comment on that. I don't know if you agree, if you have something to say. This is what I want to say about.
Oh yeah, thank you. Thank you very much for to point this out, and I will correct it in the final version of the manuscript, of course.
Okay, I'm glad you can do that because I think in some countries you cannot do the version is final, but if you can,
I can.
these minor things.
Yeah, I can for sure. I will. I will.
Okay, perfect. Okay, but most importantly in this is the contents and contribution. This work addresses and it contributes to the solution of the problem of how to teach a robot to perform some tasks by imitation learning of human actions, independently of the environment and the robot topology. Very intense. It's very ambitious.
Yeah.
I'll get back to that. Well, in this case, the actions are mainly reported to manipulation. You can replace, and I'll have a question on that later, but you still need a balanced perception of the environment, and you need also the robot kinematics to do the motion, ultimately, of course.
Yes.
But the most relevant part is you create an entire workflow, and you create the tools, algorithms, metrics to assess the results. It was a huge work. You did this in 3 years, was it, or
yes,
before?
No, it was in 3 years. But the tactile exploration strategy was started a little bit before, but I still worked on these contributions during my PhD.
Yeah,
but no, all the other works is within the 3 years.
Okay, then that's what you developed a data set allocation tool to apply that to the human 3.6 million. By the way, a short question. I have a student is working in something similar, and she had a hard time to download the human 3.6 data set.
Yes.
Yeah, was it easy because she had to ask a lot of authorizations and things like that?
Yeah, no, yes, it takes time, but once you have it, you keep it.
Yeah, that's what she did. That's what she did.
Yeah,
It was a hard time for her to get
but
this.
yeah, maybe for the 2D and 3D poses, it might be easier because you can find it here and there on the web.
Yeah.
But for the images, yes.
Yes, because of that. Okay, I'll go fast to go to my questions. Okay, I think that you did this 3D human pose estimation, and I'll have a question that later. I like the idea of the unsupervised method. That's what I'm dreaming about, because in my lab, and Patrick knows it, we have lots of sensors, cameras, lidars, calibrate. We developed a calibration system, and we call it Atom, into a universal calibrator. It works very well, but it's very slow. And this solution interests me, because I tell my students to try these alternatives. And with these representations, you extract human poses, then you want to counter challenge to teach the execution of some tasks to the robot. That's the core of your work, I suppose. And you do that imitation learning, and you do that with several variants of reinforcement learning. So I suppose that I can summarize, and I want you your outcome of this work. So we have a successful scene representation by the vision language model. I wasn't aware of that because the grounded sound that we just used here. Okay. The tactile exploration strategies, Catherine also asked this question. I was not so sure how you use them how relevant was it for what we showed you today? Okay, I have this question. How relevant was it? Because I didn't follow well the integration of the tactile in your solution.
Yeah, so it was not integrated in the main demonstration understanding and reproduction pipeline. So, okay. However, actually, these solutions were developed initially in the context of minesweeping robots. So we developed a robot that could explore the ground with just
with the rods.
yeah, exactly. And so we developed it for the DGA, the Direction Générale de l'Armement, in collaboration actually with our two teams, Patrick and Kevin. And so, yeah, we developed a lot of algorithms for tactile exploration using reinforcement learning. So I worked a lot on this during my during the PhD as well, but we didn't integrate it directly in the imitation learning pipeline. But I still think that if we could add some tactile information to the demonstration and understanding pipeline, it could be interesting. At some point, we wondered if we should, for instance, equip the operator with tactile. I don't know if you have seen the MIT, the tactile glove from the MIT, but it's very basic actually. But it allows to estimate how the exactly. So you have more information about your demonstration. You have tactile information about your demonstrations, but it's very intrusive at the same time. So and still, this version I think is still very rudimentary and very intrusive. So improving this to maybe collect tactile information in more complex environments would be interesting. Yeah,
I agree.
That's another PhD.
I agree that multimodality is the future. Actually, you are using already the 3D and the RGB. So it's already multimodality. But if you put tactile, it will be a killer solution. I'm sure. Then also another relevant outcome is the 3D pose, human pose estimation from a video, and with a time horizon of 7. Very good results compared to the literature when we need many more. But I was impressed by that. So and Univa's also challenge-based to perform the 3D annotation. Okay, that's a contribution. It looks minor, but it's important. But for me, it was relevant. And also, and Patrick mentioned that the decomposition of tasks will really better match human and robot actions. It's a good idea. I'm not so sure how easy it is, but your contributions are interesting. And in the end, you identified the limitations of your approach. You are so humble and so honest that you put them, the 3 main limitations, the simple presentation, when you say only 76% of our demonstration data set was able to be recognized. Difficulties in extracting the two orientation. Orientation. And also the need to manually annotate these are the 3 mains, and I agree with you, the 3 main. So did I do a reasonable enumeration of what you did? Or
yes, sure. Yes, I think
it's just to be sure. Okay. Just with my time here, 7 minutes to not exaggerate, because I'm just starting. I'm sorry. Okay, don't worry. This is so interesting that I will be discussing this for hours. But I think your work is very efficient. Imitation learning, agnostic to environment and to the body of the robot is solutions. I mean, the end of the question. A more philosophical question on that, but let's say at the end. And agnostic to the environment. I think it's becoming a simple and simple problem. I think because there are so many tools about the environment. You can use segmentation, you can use semantic segmentation to discover your background. You have single shot, multiple shot classifiers. There are YOLs that are fantastic in classifying your objects very fast. So I think that would not be a problem. Agnostic to the environment, it doesn't make me feel uncomfortable. It's much more challenging agnostic to the body. And I think you did that, you fulfilled the problem. It's not a question, but I want you to comment on it. Actually, you are following the agnosticism about the body is to forget the arm, just to look at the PCP or the wristband. That's the trick you use. So you are actually following the trajectory in 6D, of course, XYZ and the three angles. And that's your trick to do the body agnostic.
Yeah.
Okay. It's explained like this, it seems simple, but it's actually not. Okay. Now, going more specifically, I like the way you put your research questions. I'm starting I went back to the beginning. And it has been a practice in the latest years for the students to do research questions. I think it's a very good practice because 20 years ago, in my PhD, I did put research questions.
Okay.
But they are so well posed that I have a question for you. In which stage of your work did you define the research questions? In the beginning or after the work? You can be honest. I know the truth.
Do you want to know the initial title of this PhD?
Yes, I like it.
Bimanual task imitation learning. So you can guess at what point we actually defined and redefined again and again the research questions.
There are so many 10 research questions. It shows the ambition of your work. Some of them are maybe related to 8 and 9, I think, but that's not the most relevant. So I was considering that you did that. Okay, I'll pass some more comments, and perhaps I'll jump to the later part of chapter 7 and 8 of that. Well, I will focus concerning the primitives. Because I'm doing research course with my students. We are using also the concept of primitives for interaction with contact. And then we get a problem. I want to know if you have the same problem. And the problem is, which criteria did you use to define the primitives? Are these primitives focused on this task only, or are these primitives enough for many other tasks? Because we have a problem, other primitives, we divide 4 primitives in our contact, which is push, pull, twist, and shake. The interaction problem. We think they are enough for most of the interactions that humans do with robots, but we're not so sure. It was inspiration. We didn't see anything. So I put the same question: how do you reach these 3 primitives? Are they specific for this task, or do you think they can go further than this?
So, of course, I think they can go further than this, and I actually chose those kind of primitives because they can be used for many other tasks. Actually, I initially chose those primitives because I first looked at how to control a robot. How do you control a robot? You need to reach grasping for pick and place tasks.
Okay.
You need to reach objects to grasp them. I need to reach some position where you can release these objects. And these kind of primitives can be directly executed on the robot, right?
Mm-hmm, yeah.
So initially, that's how I chose those primitives. But we could envision some more, I'd say, evolved primitives. We are not restricted to, we could use different kind of primitives, more complex ones. Even we could, if you have some very fine manipulation tasks, I think these kind of primitives are not enough. Maybe you will need to even, I think, retrain some primitives using reinforcement learning that could be reused for imitation learning for different other tasks. And
could you do transfer learning on this? I mean, you could start with this training and then increment. I mean, if tomorrow or the day after you find that you have 2 or 3 more primitives that are interesting for some tasks, for example, for handover operations, or for complex grasping tasks, to pick tools, for instance, that are not easy, not orientation only, but more, or even precise handling a single composite object. Mount a Lego, for instance.
I see like this word primitives. I see this just as a modular thing. When the most basic primitive is just the delta position on the robot, then we can have more a little bit more sophisticated primitives, which are reaching some points to grasp or release objects, and then you can start to build more and more complex primitives on top of that by reusing the lower level primitives. That's how I view primitives actually. So you can, it's a never-ending task.
Okay, I'm looking at the time, 20 minutes already. A question, I think you mentioned it because I'm curious about it. In the training, how does the velocity of reaction influence that training?
Of course.
Because, I was wondering if I want to do the same task faster, would this training be possible, or would it result well in the robot?
Yeah, actually, for regarding the velocity, I think of course we can analyze the speed, the velocity of the human operator in the demonstrations. So I think it could be straightforward to extend our pipeline to incorporate some speed or velocity understanding and reproduction on the robot. However, there is one thing that is much more harder is the torque. If you want to control your robot using a torque, for instance, for a sending task or for in this way, it's way harder to collect human demonstrations, at least without having intrusive equipment. For instance, for a standing task, you could equip the operator with yeah, exactly. I presented the glove. If you want to have tactile feedback to know how strong you are prehenting your object to lift it, for instance, you could use tactile gloves, but then it's more intrusive and it's less easy to collect.
And simulators are not good enough to create those. I'm saying that because I have a student working on this using a remote simulator is having a hard time to.
Yeah, but by the way, there are vision-based solutions to estimate the tactile prehenting. So just by filming like a person grasping an object and lifting it, from vision, you can try to guess how hard the person is actually.
It's a new world.
It's an entire topic. Yeah, it's a full topic. Yeah.
Okay, this is before my final question, because unfortunately I have to respect the time with my other colleagues. I just a question. My students are using the media pipe extractor of it's fast, it's quite reliable, but it has a frame rate so fast that it fails 20%, it's still faster than this pyramidal approach that you use.
Yeah.
Did you try the media pipe? And did you like it?
No, no, I think it's way less accurate than using HRNet from the original library, or even MMLab. If you can use alternative MMLab, it's a full lab for object detection, tracking of the joints and so on.
Because we showed the tracking and media pipe in tracking, and it's very good to come to a 3D.
Yeah, of course. Yeah, for quick prototyping, you can try. But if you want a very accurate 3D reconstruction, I would suggest to move to OpenMMLab and especially to MMPose, in which you can have access to a wide range of existing solutions, including HRNet and other kind of.
Have you do the frame rates in different time?
It depends because you have a wide range of models, more or less heavy, and then of course the heavier, the slower. So yeah, I would say.
Okay. Last one. It's one. Okay, this is a provocative question. My final provocative questions, and there are many studies that support that the real physical systems need to have a body to develop an actual biological-like intelligence. Look at humans, the bipedalism, the openness of the tongue help developing our intelligence. And also the current trends in cyber physical systems. You need your intelligence, but you have a body. Your work focused on and body free. So, are you in counter cycle, or how do you frame or put your work inside this new context of embodied AI approaches? This is more philosophical question because I imagine that you have applications of your case, but philosophically, I think this is a question. Normally, we need a body to develop an intelligence. What's your point of view on that, and how does your work fit in this?
Okay. So yeah, no. Actually, maybe this is not the answer that you would expect, but a long time ago, actually, I read a paper about it was Ilona Kovacs. I don't know if you know. He's a researcher. I think it was like in understanding, how do we say this? But anyway, she showed like in children, like there is always this development of the vision cortex that develops first, and then the motor cortex follows. And then the vision cortex, since you can start to move in the environment, your vision cortex will acquire more information. And from this information, you understand more things. Then you can start to interact in a more complex way with the environment. And this iterative learning with the cortex, vision cortex being in advance always a little bit compared to the motor cortex, I think it highlights that you can still you can develop a first kind of intelligence just by watching and analyzing the scene. But then, if you want to understand better your environment, to be able to, of course, understand how the environment would react to interactions, then you need to be embodied. So. And this is really funny because when I read this paper, it directly made me think of the dreamer model from, I think was it OpenAI or DeepMind that developed this model? It was very similar, but in the deep learning world, actually the dreamer is actually trying things in the environment, then watching what happens, and then learn to dream about what he did in order to achieve new behaviors and collect new information about his environment and loop like that again and again. So, but I truly think that you can develop an intelligence by just watching the environment, but not as complex as if you were interacting with the environment. So that would be my answer.
It was just thank you very much for the work and for being here. Thank you.
Merci beaucoup. Je vais pouvoir laisser la parole à M.
Merci pour la présentation. D'abord, je veux également remercier l'équipe encadrante pour l'invitation à la lecture de vos documents et suivi de toute façon le déroulé de vos travaux depuis la première année. Donc, je suis content de voir finalement la finalisation de tout ça. Et les différents développements, les derniers développements de travail. Donc, sur le document, je rejoins ce qui est écrit, il est très conséquent, il y a beaucoup de contributions, beaucoup de choses. Et le choix que vous avez fait pour votre présentation, d'extraire, il y a deux contributions de vos travaux. On ne peut pas le reprocher, hein, c'est le choix que vous avez fait. Du point de vue du roboticien, je ne sais pas si j'aurais fait ce choix-là. Bon, je vais poser des questions un petit peu générales parce que je vous ai eu le temps de poser plein de questions sur vos travaux de manière très particulière. Et donc, je vais essayer de poser des questions générales mais pour ne pas prendre trop de temps non plus. Bon, une première question porte, c'est génial, hein, c'est sur l'ensemble de vos travaux. Comme je l'ai dit, il y a beaucoup de contributions et voilà, donc il y a un point d'interrogation un petit peu moi, que j'ai ressenti à la lecture du document, mais également lors de votre présentation. Finalement, c'est comment vous vivez tout ça. Alors, je l'explique, alors je prends l'exemple de la présentation, on a une première partie qui fait du calcul de pause sur les... qui fait du calcul de pause sur les opérateurs, là. Et finalement, dans votre stratégie d'imitation, ben, il n'était pas utilisé. Alors, on ne va pas se mentir.
On va pas se mentir.
Donc, voilà, là, alors, je vais décliner ça sur l'ensemble en fait, des contributions. Je prends partie aussi, moi, qui m'a bien intéressé sur le volet tactile. Et ben, finalement, on aurait pu se dire c'est quelque chose qu'on va en rediscuter. C'est très intéressant pour justement cet aspect imitation des gestes opérateurs dans un contexte qui peut être un contexte industriel, comme vous l'avez motivé au départ pour le contexte. Et finalement, il n'est pas utilisé. Donc,
Alors,
ouais.
Alors en fait c'est deux choses qu'on a développées quasiment en parallèle. Avec, comme je disais tout à l'heure, en fait, on avait toute la partie estimation de pose qu'on a commencé à développer pour estimer la position de l'opérateur dans la scène. Et en fait, comme je disais tout à l'heure, en fait, on avait tout un pan de nos activités qui était relié à l'estimation de l'ergonomie de l'opérateur. Donc effectivement, ça, je ne l'ai pas forcément relié par rapport à notre pipeline d'imitation. Mais en fait, tous les algos qu'on a développés là, bah, c'est ce que je montre dans la perspective. En fait, ce genre d'algo, ils peuvent être utilisés aussi pour traquer la position de la personne dans la scène pour une application à imitation learning. Alors en fait, pour la petite histoire, j'avais collecté des données multivues. Bah, en fait, je les montre, je crois, là, dans mes tac tac.
Je suis tout à fait d'accord que c'est super intéressant pour l'imitation learning.
Voilà.
La question
On
est
avait.
plutôt pourquoi vous ne l'avez pas intégré à vos.
Ouais, alors en fait, on l'a investigué pour le coup. Euh, J'avais collecté des données avec un setup multivue sur lequel on avait différentes caméras RGB et des caméras 3D qui filmaient notre scène. Donc en fait, ici, on voit un des points de vue RGB qui filme une personne en train de mettre des chaussures dans une boîte. C'était la tâche qu'on avait choisie. Et ce qui se passe, c'est qu'en fait, on voulait utiliser la caméra 3D pour avoir une représentation de notre scène. Alors, attendez, je peux peut-être switcher pour vous expliquer ce qu'on avait fait. Je pense que j'ai un transparent là-dessus.
Oui, après, de toute façon, le choix de la caméra 3D me semble tout à fait logique.
Ouais, ouais. Non, mais c'est juste pour mettre en avant que, en fait, sur ces données-là, on a eu un souci, c'est qu'en fait, comme dans nos scènes, on avait des surfaces très uniformes, on s'est retrouvé avec une caméra 3D qui était inutilisable pour estimer les nuages de points de notre scène. Donc là, d'ailleurs, on a investigué tout un tas de modèles de deep learning pour essayer de reconstruire la profondeur de la scène. Donc, dans certains cas, ça marchait et ça nous donnait une belle représentation de notre scène avec une belle estimation de la pose de la main qui était triangulée à partir des plusieurs vues. Donc là, on a une reconstruction de la main qui est quand même très propre. On avait bien nos nuages de points qui étaient estimés à partir d'une carte de profondeur reconstruite avec un réseau de neurones. Mais dans certains autres cas, en fait, l'estimation de profondeur par le réseau de neurones ne fonctionnait pas du tout. Donc, en fait, ces données-là n'ont pas été directement exploitables pour faire de l'apprentissage par imitation. Et du coup, là, si c'était à recommencer, je pense que j'investiguerais quand même encore ce genre de solution où j'aurais une caméra 3D, mais cette fois-ci, pas une caméra stéréo simple, une caméra stéréo avec projection de frange ou avec un lidar pour pouvoir travailler sur des surfaces uniformes. Et j'aurai quelques points de vue en plus autour pour pouvoir trianguler proprement la position de la personne dans l'espace 3D, quoi. Donc voilà, en fait, on l'avait investigué, mais on est tombé sur des os, c'est normal. Donc on a continué à investiguer d'une autre façon, en parallèle de ce qu'on investiguait sur l'estimation de pose humaine. On a continué à investiguer les deux en parallèle. Donc effectivement, maintenant, il manque l'étape suivante, c'est de réussir à réintégrer les deux. En fait, il faudrait recollecter un peu de data, comme je viens de dire. Je pense avec une caméra 3D amovible, parce qu'on a démontré que c'était important, et quelques petits points de vue autour qui permettent de reconstruire bien précisément la pose de la personne. Et on pourrait très bien imaginer ça être intégré sur un robot, avec le robot qui nous fait bouger automatiquement notre caméra 3D pendant les démos, et quelques points de vue fixes autour qui nous servent juste à faire de la triangulation, en fait. Je partirais peut-être sur une plateforme comme ça. Après, ça serait, si on devait repartir, j'imagine que ça serait à rediscuter, mais voilà.
Ok, ok. Euh, euh, Toujours un petit peu dans cet esprit-là, vous indiquiez donc, bon, c'est le titre de test que vous expliquez très bien dès le départ, décortiquer. Euh, et là-dedans, il y a une notion d'indépendance vis-à-vis de l'environnement, hein, et puis il y a une notion d'incarnation aussi, hein, des mouvements. Alors moi, je ne sais pas, je trouve que euh, c'est un peu un abus de langage, de dire que c'est indépendant de l'environnement. Je parlais plutôt de la géométrie de l'environnement, parce que l'utilisation que vous faites de la vision, c'est de l'extraction finalement géométrique. Et exemple, très simple, enfin deux exemples. L'environnement, c'est aussi, je sais pas, je suis dans un contexte où j'ai de chambre froide,
Ouais.
où j'ai un contexte où c'est venteux, ça va modifier l'environnement et ça va modifier la manière dont est réalisée la tâche par la personne opérateur qui
Ouais.
la réalise, finalement. Donc, plus que, alors, je ne sais pas ce que vous en pensez, mais pour moi, ce n'est pas de l'indépendance vis-à-vis de l'environnement. Si j'avais à peut-être qualifier ça, ce serait plutôt des notions de géométrie. Alors même, vous avez très bien expliqué sur les aspects effort, par exemple. La vision ici ne le permet pas. Donc, alors, je vais vous laisser vous exprimer un petit peu dessus, parce que c'est assez intéressant, parce que finalement, la question, c'est avec ce type de développement, finalement, quelles tâches on est capable de réaliser?
Ouais. Alors, du coup, pour répondre à votre question, c'est déjà sur est-ce qu'on est agnostique à l'environnement? Effectivement, je le dis même dans ma conclusion, on est partiellement agnostique à l'environnement. C'est-à-dire qu'effectivement, du coup, on est agnostique à tout ce qui va être à l'aspect géométrique et visuel,